Hello everyone. Today we will solve this numerical problem. We will use the control system theory to solve this problem. They have given that there is an op-amp and it have two poles and one RHP 0, and they have given the 0 location is 10 times the gain bandwidth. They have also given phase margin is 60 degree, and they have asked where is the second pole. So we know that this problem is related to two-stage op-amp because two-stage op-amp also have two poles and one right hand 0. Okay, so I have attached one schematic which I have designed in my cadence. I'll later make a video how to design a two-stage op-amp. So let's first solve this problem. So we can write the transfer function for this op-amp. So it have two poles and 1 0 contributed by this Miller cap. So we can describe this op-amp by a transfer function as DC gain into 0 location 1 minus s by omega z1, since it's a right side 0, and 2 left pole. Okay, so now we will write in frequency term. So replace s to the by j omega. So here ADC 1 minus j omega by omega z1. Similarly, and this will also come. So now we will see magnitude and phase contributed by this op-amp across all frequency. So the magnitude will be across all frequency given by this term. So at different frequency, it will be different magnitude, and phase contributed by this op-amp across frequency will be this one, tan inverse minus omega by omega z1. Since poles are in denominator, so they will come as a negative, and 0 is a right side, so that will also contribute negative. So all three term will become negative. Now they have given phase margin is 60 degree. So phase margin is plus minus 180 degree minus angle contributed by this function at omega u, unity gain frequency. So depending upon your reference here, you may be plus minus 180 degree. So I am going from 0 to minus 180 degree. So my reference is minus 180 degree. If you are going to minus 180 degree to 0, so your reference will be 0 degree. Okay, so at omega equal to 0, my phase is 0, and at my omega equal to unity gain frequency, my phase contributed by this transfer function will be minus 180 degree. So the difference will be 60 degree. So with respect to minus 180 degree, if I have 60 degree of phase margin, then this transfer function must have contributed 180 degree of phase shift at omega u. So you write the put the value in this phase margin. They have given 60 degree, and my reference is minus 180 degree, and at omega u my transfer function will give then minus 180 degree of phase shift. Okay, now here we will take one assumption that our two-stage op-amp is uh, properly compensated, and finally it will behave like a first order system. Okay, so my unity gain will be near about gain bandwidth product, since a one single pole system. Okay, and my gain bandwidth will be much higher than the pole location, first dominant pole location. Okay, and they have given my 0 location is 10 times the unity gain frequency or gain bandwidth. So let's put this value. Okay, so here uh, angle contributed by this total term should be minus 180 degree. Okay, so I have taken, when you put this value, then it will be minus will be cancelled out, and it will become 180 degree. Okay, now omega u is near about to gain bandwidth. So I have taken omega gb. I am calculating phase shift at gain bandwidth frequency. Okay, so put omega equal to gain bandwidth. So omega equal to omega gb. I have put in, then I am using that condition. Okay, so the gain bandwidth is much higher than the first pole location, so it will be nearly infinite. So the phase shift will become gain bandwidth by omega z1 plus this term will become 90 degree infinite, so that phase shift contributed by this term will be 90 degree. Okay, and rest of the term are same. Now from here you will get this term. Okay, now again they have given the second thing, that zero frequency is 10 times the gain bandwidth. So now here we will see gain bandwidth divided by zero frequency will be 0.1. Now this we will put this term into this one. Okay, after putting value we are getting tan inverse gain bandwidth by omega p2 equal to 30 minus tan inverse 0.1. That will come to 24.29 degree. Okay, from here if we will take tan of both sides, so we will get gain bandwidth equal to tan of 24 into 0.29 degree into omega p2. So my gain bandwidth is coming out at 0.45 omega p2, and from here second pole location will be 2.2 times gain bandwidth for phase margin of 60 degree. So we will use this concept in design of two-stage op-amp, because in that also we want 60 degree of gain margin. So we want to know where should we put our second pole so that we get a phase margin 60 degree. So here we can see that. So the first thing is we have to put the our zero frequency is at 10 times of gain bandwidth. So my pole location will be 2.2 times of gain bandwidth, and now we will get phase margin of 60 degree. So if these two conditions are we are getting, then our op-amp will have of 60 degree. So now here if my zero location is 10 times of gain bandwidth of this op-amp and my second pole is 2.2 times of zero frequency, then we will get a phase margin of 60 degree. Okay, so watch this video, and if you are getting any doubt then comment, and if you want this PDF then comment your Gmail ID. I will send in at that mail ID. Okay, and after some time I will give a video on how to design a two-stage op-amp. So if there is any doubt, please comment, and you want if any topic and design numerical, then tell me. I'll try to make a video. Okay, thank you.